Hello everyone, welcome to my talk, Unprivileged Containers, Shaving Yaks to Get the Toothpaste Back in the Tube. Just a word of warning, this talk is basically equivalent to the movie Speed of Keanu Reeves and Sandra Bullock fame, that basically if I drop below a certain number of slides per minute, the narrative arc will explode. So sorry for talking fast. So who's this internet goth? So my name's Matt. I'm a tech lead on the incident detection and response team at Yelp. I've been at Yelp for 10 years. Yelp is a company whose mission is to connect people with great local businesses. So moving on. So basically, my career arc thus far has been basically I've gone from sysadmin to site reliability engineer to security. And I've spent most of my time at Yelp now. I was originally on the operations team before it was 4 teams and called production engineering. But I've basically been on 3 security teams at Yelp. And basically, like, infrastructure is my hammer. Everything looks like a nail. So that's to kind of contextualize why I solve problems in the way that I do. Now, you might be asking yourselves, as many people come up to me in the street and ask me, Matt, what does container security have to do with incident detection and response? And the answer is exactly nothing. We formed the team at the beginning of the year in January, and I finished the project, this 1.5-year-long project, in March. So it's basically just a huge non sequitur. So before we get started, I basically want to go into some definitions here. So at Yelp, we have a bit of communications guidance because we have so many people from different backgrounds, different countries working there. We basically advise not to use too many idioms in the way that we communicate. So I've breached that cardinal law already. As I like to a lot, one of my favorite things to do is to actually use the idioms anyway and define them. So that, like, finding out idioms from different cultures is a fun thing, right? So to start off with, we've got getting the toothpaste back in the tube. If you're like me, you might spend a Saturday evening going, I'm very bored, I'm going to squeeze all of the toothpaste out of the tube. And then in a blind panic, realize that on Sunday morning, I need to brush my teeth. So spend the rest of the Saturday evening designing apparatus, creating a huge mess to get that toothpaste back in the tube. I like to think this one's pretty self-explanatory, but at the end of the day, it's the idea of something that you might do that is incredibly difficult to reverse. There's a huge asymmetry there, right? Shaving yaks. This one's a lot more difficult. I'm not really going to explain it very well because the canonical example is something like you need to wash your car, but the hose is broken, so you need to go to B&Q. Several steps later, you're chasing a yak round a field with a razor. But it's basically this idea of a seemingly unrelated task that you need to do that's kind of dependent that you need to do in order to actually achieve your main goal. So you can see how we're talking about asymmetrical effort and getting right off into the weeds. And finally, what I want to define here is just, right? When I say just in air quotes like that, what I actually mean is it was terribly difficult and I don't have time to go into it right now. This is like fractal complexity we're talking about here, and I've got 45 minutes, which I'm wasting a lot of. But basically, it's also the crux of the narrative that threads through this story, right? I've been given the advice, just use rootless containers. And basically, that word just, it glosses all manner of sins. We'll come back around to this later. Anyway, actually moving on to the talk. So the agenda here is I'm going to talk a little bit about context, the who, what, why, and whence of basically the kind of infrastructural setup that we have to start off with that gives us the problem that we've got. Then I'm going to go a little bit into Docker and permissions, so ultimately defining why we have this problem, where this problem really kind of comes from technically. Then we're going to go briefly into the theoretical solution, which I think is like all of like 2 slides, because theory is nice, right? But then we're going to spend the majority of the talk on the Lovecraftian hellscape, which was implementation. This was originally supposed to be a 6-month project, by the way. It took 1.5 years, and the year's off the end of my life. And then we'll go into some reflections and lessons. But needless to say, this is a story about where theory meets implementation, and they have a big old war of attrition. My final caveat here, this is not technical advice, right? Basically, I'm going to talk about some technical concepts, which are totally reusable, remixable. But fundamentally, I'm not telling you do this exact same thing. What I'm saying here is we had a thing we wanted to achieve. We had a bunch of trade-offs that we were willing to make with regards to it. And our priorities were around restoring those security paradigms without disrupting developer velocity. It's deeply reflective of who we are and what we were doing, where we came from. But the idea here is that this is basically, sometimes you really need to apply security in the context it's in, right? So the who, what, why, and whence, and I won't spend too long on this because I'm sure you don't care that much. But basically, Yelp runs microservices, which is a lot more impressive when you said it 10 years ago. But basically, we started out with a monolith, then statically deployed microservices, and then we built a PaaS called Pasta. The TA stands for totally awesome and was absolutely not backronymed. But basically, I'm sure you're thinking, why not just use Kubernetes? Well, it wasn't invented yet. So we basically built this thing out of Mesos, Marathon, and Docker, right? And we were running Docker in production when the website still said, you probably don't want to run this in production. So our PaaS basically dictates a contract for how containers should behave, right? And it comes with associated development tooling. The fundamental idea here being that the majority of our developers are writing HTTP services that interact with each other. So let's build a platform for that 80 of the 80-20 rule. So effectively, this development tooling, it was very much about developing on containers. That whole let's ship your machine to production then, and fundamentally it works for developer velocity. It works really well, and especially if you build a bunch of tooling around those workflows to get rid of the really common tasks like instantiating networking, like pulling and launching dependencies, running acceptance tests. So it was basically to deduplicate a bunch of that effort to remove a bunch of the inconsistencies. So we're using this tool, which we invented internally. It's called Yelp Compose, right? I want to say we. Other people invented this bit. Other people did the development tooling, right? So Yelp Compose, or YCP, is heavily inspired by Docker Compose. It just removes a bunch of the bells and whistles to kind of say, here's the default thing. It just works. Now, the keen-eyed of you might have noticed here that, in fact, the bit which I didn't say out loud, we have shared development infrastructure. So we've got multiple developers running on dev boxes, right? Multi-tenant. So you might have noticed here that I'm saying we're all developing on Docker, and there are multiple people on each machine. And you'll notice as well that this ticket was created about 5 months after I joined the company, and I closed it in March this year, short of its 10th birthday, right? And this is basically somebody realized, holy shit, we've done all of this, and actually it turns out that anybody can root a dev box now. Which sucks, right? And if you don't believe me, I'm an idiot and have decided to do a live demo, so I just have to find where my mouse has gone, and I have to do this. And that's, so basically what you can see there, look at the last lines here. So Echo Docker host is there just to prove that this is using default Docker socket. It's running on a privileged Docker, right? So this command is basically, I'm running just an Ubuntu container. It's mounting my home directory as a volume mount. It's then running bash. It's copying bin bash to my home directory in the volume mount. It's schmodding plus s, and understand that Docker runs as root by default, right? That bin bash, and then I'm basically able to run that who am I. So root, I am root. So effectively, what we've got going on here is that one thing that everybody in security says you shouldn't do. This is not least privilege. And basically, to sort of just make sure that that's fully explained, that bash binary, I was able to say, run this as the owning user. Outside of the container, the owning user is still root. So why is this an issue? So fundamentally, this is an issue for more market-driven reasons than anything else, if you ask me. So basically, Docker was kind of the first to market in terms of that development containerization, right? It's not the first ever containerization solution on Linux. It's not the first containerization solution, full stop. However, the first thing that it did do is it presented that Docker file, and it really focused in on, you can develop this thing, you can have your development environment, you can build your build artifact, you can ship it to production, and it will just work. And largely that's actually a just that is not so terrible, because it kind of does. I mean, if you ignore all of the engineers who put together the platform, but never mind. So basically, the issue here is that in order to get first to market, they've basically made it very easy to develop and very easy to iterate and move forward by removing a lot of the blockers, like needing to have permissions to do all the things that you need to do. So fundamentally, the issue here is that, so you can see here this Docker engine. This is the Docker daemon, Docker-D, right? It's just an opinionated HTTP server that does a bunch of tracking and other things, but it uses the containerd runtime. Docker, the command line, is just an HTTP client. So it's talking over a socket to Docker engine, or Docker-D. This talks to containerd and tells containerd what you should do. Containerd then defers to containerd shim, which is basically manages each individual container and controls the actual workload itself. So like forwarding back standard in, standard error, controlling signals, stuff like that. And so here we have an example that's very, very difficult to read, but that I put together specifically for, to sort of demonstrate this. So this is something I did yesterday. This is using an internal log source, by the way, that we have called PidTree BCC. If you want to learn more about that, search Carroll DevSecCon 2019. We've open sourced this. This is an eBPF tracing solution. So the idea is that for any internet-bound TCP connections and also other traffic, it logs the entire calling process tree, which is also called winning a race condition, which we win all the time, which is nice. But basically, you can see at the top here, or if you can't, I'll explain it, curl44con.com. You can see that's reaching out to 44con.com, the IP address. Username is nobody. On the next level down, we've got containerd shim. Username is root. Next level down, systemd. Username is root. Now, the only reason that username is nobody there is because I told it to run as nobody. By default, it will run as root. And this is fundamentally the issue. Everything in this stack is running as root, and the user talks to it over a Unix domain socket. So basically, privilege dropping in the container is left up to the user. There's a lack of, I mean, this is not even the icing on the cake. The icing on the cake is that there's a total lack of coherent local auth-z and lack of useful logs. So the only way to authenticate to the Docker domain socket, if you set it up, is MTLS on a local Unix domain socket. It's like, local Unix, let's use X509 because it's nice. When in fact, actually, in Go, it's just that one line to get the calling process's credentials. But basically, Docker doesn't map authenticated users to containers anyway. So you'll have this fleet of containers running. There's no tracking who launched what. I mean, it doesn't know in the first place. And even worse than that, auth-z plugins exist, to be able to say, to call out to Open Policy Agent or something like that, and say, don't allow this sort of action. But the thing is, there are no built-ins for path traversal or multiple mount options. So it's like a game of whack-a-mole, right? You can do Docker plugin disable on the auth-z plugin, and it'll just turn it off. Basically, due to socket communication, even if you're using something like a mutable login UID, that information is lost because it's just going onto a different process tree. Docker doesn't log any part of the command. Containerd doesn't log the ID of the shim until it kills it. So the TLDR is access to the Docker socket is root without audit. So the theoretical solution. So what we're asking ourselves is, how can we converge the list of privileged users to the ones that are actually defined in auth-z policy? So to put it another way, how do we let our developers continue developing a containerized solution, but then only allow the people who are supposed to have privilege have access to that privileged Docker socket? So we're just going to use rootless Docker. The way we're going to do this, unprivileged user namespaces. So Linux containers are basically made up of multiple different types of namespace: network, mount, inter-process communication. Unprivileged user namespaces allow the translation of UIDs. So if your UID not inside the container, if you're using unprivileged namespaces, what you can do is you can say, so my UID is 1337. Inside the container, I want that to be 0. For the full range of other UIDs that don't apply outside the container, you might say, OK, well, we're going to use the mappings in etc sub-UID and sub-GID. So the way that that's actually kind of formatted here, well, you can't see that pointer at all, so it doesn't matter. Basically, it's username, colon, the start of the sub-UID mappings, colon, and then the amount of sub-UID mappings that there are, so contiguous, right? And what these are, they're just like really high number UIDs that aren't used in normal system usage. They're only for unprivileged user namespaces. This basically means that you can map an entire Unix system's worth of kind of fake UIDs that belong to a user into that container. So fundamentally, this puts us in a position whereby if you can execute a container escape, you have an escalated privilege. And in before, unprivileged user namespaces can cause privesc, yes, if there's a kernel vulnerability. At the moment, we don't even need one. So it is actually a massive improvement of the security posture here. So this is a diagram from the original design document when I was solutioning for this. And fundamentally, like what I'm getting at here is so that top A, unprivileged Docker, that's saying, OK, well, what we're going to do, we basically, so B is privileged Docker. B is like, we're going to continue to run that system level, right? And that's for the sake of people like myself who might want to do some weird experiments, your sysadmins, the people who are going to build weird stuff in containers that might actually need privilege, but they have privilege. The unprivileged stuff is basically going, we're going to run a Dockerd per user, but we're going to run it inside an unprivileged user namespace. The result of which means that if a container escape is executed, it's just into that user's UID, right? You don't immediately get root. The hard limitations of this are effectively no listening on ports below 10 to 24. Good. No accessing files you don't have permissions to. Good. Networks can't be routed to or from the host without setting up roots on that host level. This is basically because everything there is running inside a network namespace. This is not ideal for usability, but it seems like the sort of thing that we can sort of code around, right? Also, as a sort of side note, no SSHing into containers without a PAMD patch, because effectively we're making it so that the Dockerd now has a login UID set, and we use immutable login UID on our system. So it means that anything that would try and set that login UID will not work properly without a PAMD patch. But basically, the network stuff's a little bit annoying, but the rest is very good, which is obviously nice in theory. And to give you a feeling of what's about to come up, this is a slide from an internal talk, which I did when we were about halfway through the project. So segueing on to the Lovecraftian hellscape of implementation, the first problem that I hit upon, disk concerns. Dockerd is selfish. It's fundamentally single tenant, right? So rootless Docker basically means running a less privileged Docker per user, each with their own storage backend. Like Dockerd doesn't have a concept of, OK, multiple Dockerds, one storage backend where we track permissions. It doesn't do that. It's done an end run around that problem, which basically means n users means n copies of every used base image, right? Each of our dev boxes typically has like 10 to 20 users. Some have more. And they tend to be working on common things, which means that we're actually talking true duplication of these images, right? And we use pretty heavy full-fat base images for a bunch of our stuff, and we tend to pre-pull them to speed up the developer workflow. So we're talking a pretty big disk cost. It gets even more difficult because we still don't know how much disk costs. Even if you know how big the images are and like how many that you'll use, because the storage backend is using typically something like overlay-FS, so like a copy-on-write file system, there's deduplication of a bunch of stuff that's going on there. So the way that these file systems fundamentally work is, so like layer 3 will be your oldest layer, so like your first instruction in your Docker file. So if you look at that, you can see file 2 there. It's also in layer 1. Basically, what that means is on a subsequent instruction, something's modified that file. So what the operating system does is it basically copies that file and then modifies it. So effectively, when that file is read or accessed in any other way, the kernel's basically looking at what's the topmost version of this file, will present that to the user. But basically, like, each layer is consistently hashed to uniquely identify it. And as layers are read-only, because they're copy on write, like, common layers can be deduplicated by that mechanism. So like I say, it's really difficult to estimate. And in situations like this, sometimes the best thing to do is to go, OK, this is going to be a lot of work even to figure out. So let's do a back-of-the-envelope calculation to understand, is it worth trying to go down this route, to go, like, shall we just throw more disk at the problem? Because disk is not as cheap as it used to be before the cloud, right? So I did a back-of-an-envelope calculation of adding approximately 1 terabyte of EBS to each machine, and it came in at hundreds of thousands of dollars per year with no guarantee that my calculations were right, that it would solve the problem, or that those costs wouldn't increase going forward. So we go back to the problem. And one of the things that I like to do in these really difficult situations is look and see, does the problem have anything that works in my favor? Consistently hashed, and layers are read-only, right? So I had this idea, and like a lot of my best ideas start off with me saying, hey, OK, here's possibly totally insane idea which I haven't thought about for very long. But basically what I decided here is, could we fool Docker into thinking that each of these Dockers think that they're managing all the base images, but they're actually read-only and they're deduplicated, like bind-mounted in, or symlinked, or you know, overlay-fs on overlay-fs, or something like that. And that's a really nice idea in theory. But turns out life doesn't work like that. And I just tried this in multiple different ways. That buries all manner of sins. And what I found myself wishing was that, like, wouldn't it be great if Docker had some concept of an additional image store, a read-only one, into Podman? Because when I was kind of losing my rag with this a little bit, I discovered that Podman actually does have a feature called additional image stores. So Podman is another containerizer. It also uses OCI containers, so the build artifacts are the same. You can basically take something that's built by Podman, run it under Docker, something that's built by Docker, run it under Podman. It also has a compatibility API for interop with Docker, despite the fact that it doesn't actually require demonized usage, right? And basically, like, images pulled in or built by the user can still be based on those read-only images in additional image stores. So basically what I'm saying here is that red ringed bit there, we're kind of saying, like, imagine here that this is the additional image stores. You can't touch that. You can't delete those images. But you can base your file system layers, copy and write on that stuff. So we could deduplicate all of those pre-pull images. So that's basically what we started to look at. And to sort of give you a bit of understanding here as well, like I say, Podman runs in a daemonless mode. So basically, by default, if you run Podman run something, that's not an API client. That's actually a program that then launches stuff as a child of that process, which is great, because then we get to track login UID again, which is real nice. Whereas compared to Docker, you know, there's the Docker CLI talking to all of this stuff. Now, the issue here is that, like, are we really going to have to retool all of our stuff to then use Podman instead, like Docker Compose, Yelp Compose, Docker Client, Python SDK? Well, actually, this is my most artfully put together hacked graphic. So basically, we decided, well, what we can do is we can use this compatibility API, right? And this means that the Docker CLI should still work. It should still just function, which is obviously nice in theory. Because actually, we still have permission problems, even with Podman having additional image stores. Because the issue here is that we're going, OK, well, what we're going to do, we're going to use a system user, unprivileged system user, to pull in all the images. We'll use the Ubuntu user. But all of these files still belong to the Ubuntu user. So when the Ubuntu user pulls in an image, they will have an image that has, like, you know, they'll be using their UID mappings, right? So they'll pull in an image that has an etc shadow file, right? Mode 600 belongs to root. Outside of the namespace, mode 600 belongs to Ubuntu. Matsy still can't read that file, right? We additionally have the issue here that we can't schmod or chown these files because this is actually going to change the way that they function within the container, creating a disparity between the development artifact and the thing that you deploy in prod. And that's a huge no-no because basically the development version, that'll work, that'll allow anything. When you root, everything's easy, right? But then you'll deploy it and nothing will work properly. So by default, Podman deals with this, like the permission issues, by schmodding at runtime. But again, you still can't schmod at runtime if you can't read the original file. So what we want is something that can transparently translate UIDs inside the mount namespace. So basically what happened upon here was ID mapped mounts. And this is where this really starts to go into good timing. Like, we could not have done this project before we did. Like, and I know 10 years is a long time, but this solution would not have worked any earlier. And the reason for this is a feature called ID mapped mounts. So this basically does roughly what the namespaces do. You can see here, what I'm saying is the original copy, we can then do a bind mount of that with ID mapping, and we can supply what mappings we want to use. So we can say, OK, anything that's got the UID for Ubuntu, let's make that MATC. For anything that's Ubuntu sub-UIDs and sub-GIDs, let's make those MATCs sub-UIDs and sub-GIDs. And we can do this for every single user because it's just a bind mount. It's not actually copying the files around. It's just a read-only reference. And this is great and all, but ID mapped mounts weren't supported as a lower layer of overlay 2 until kernel 5.19. The most recent Jammy LTS that we were using was 5.15. Luckily, this happened to be, I think this was maybe in like January of 2023, and I was asking around and trying to figure out how we were going to work around this problem. We were going to have to backport things or whatever. And somebody in Ubuntu Security IRC told me that actually, with the next release, Lunar Lobster, that was going to have a 6.2 kernel, and that would automatically be backported for Jammy. So this was part of the AWS rolling release kernel. And you know, so this was just great news, right? Bearing in mind that this feature was so new that we had to package up the example program that the kernel developer had used in order to demonstrate this while submitting this as a patch to the Linux kernel, because the mount options weren't in the mount command yet. So we have a simple solution. Well, this is basically what happens when my boss tells me to boil an ocean, is he gets what he paid for. So to go in a little bit deeper here, base images are pulled in by Ubuntu. These are mounted read-only into var UCS UID B and ID mapped for the user's sub-UIDs on login, right? We use systemd for this, which I have some regrets about. And the read-write images are stored in var UCS UID/P, right? And those read-write layers, they can deduplicate like the layers below on those read-only images. We also just wrote our own solution for cleaning base images once dependent user images were removed. Now, you can normally do things like Docker prune, right? But the Ubuntu user's container storage does not know about those dependent images. So we actually had to do something that would walk the graph, do all the cleaning, make sure that things that were still dependent would not be cleaned up. By just, I mean we wrote it, fixed it several times, and then rewrote it again in Go to make it faster. Now, you might have noticed these kind of arcane paths. The reason I point this out is that I have a tendency towards overly descriptive names for things and then shoot myself in the foot when the scope widens and it doesn't make sense anymore later. So I'd named these var, in fact, I think it was deeper. I think it was like possibly even in the home directories. And it would be unprivileged container storage, UID, then it would be like base images or like per user images. We hit upon a bit of an issue in all of this. That basically, with one of our largest images, that original monolith that I was talking about, it would build, and it would build, and it would get to the 44th image and consistently crash and complain, this file from the last layer does not exist. Now, it turns out that Linux mount options, when you're doing a mount, all of the options for that have to fit in a 4K Linux kernel page size. And with my hugely descriptive prefix directories on all of these layers, it was padding out the entire 4K such that you could only fit in 44 layers. Now, there was a fix for this upstream for Podman 4, but the thing is that Ubuntu LTS ships Podman 3, and upstream are not interested in your problems if you're on Podman 3. So we could have backported a fix. It was kind of a bit complex. So what we decided to do instead was just make this prefix really small, and now you can get 72 layers in, and nobody's ever hit that limit, so ain't worried. So disk problem solved. Moving on to network. Network problems were not so difficult. So like by default, Podman for a single container uses slurp for netns. It just like listens on the forwarding ports. It's fine. It just works. But the thing is, when you're actually setting up a container network, you're saying, I'm going to spin up some containers later that may need to like have traffic forwarded to them and everything like that. So what we came up with was setting up some mixed privilege stuff. So having a privileged systemd daemon that on user login is able to set up this Yelp Compose network for you. Because like using the Yelp Compose tooling, originally was that our configuration management would set up this Yelp Compose network, single one, all the developers on the machine were on that network. So what we do instead is we just set up this network ready. And we basically set up a container that kind of wedges the network open because Podman wants to be in charge of the network, and if there's not a container, it won't hold it open. But once we've got it open, we use a process in that network namespace to target, to jump in, insert one end of a V pair, and do all the routes, set the default routing to go through that instead, and do some natting and routing on the host. So basically, what we were doing here is we were saying generic container networking will not work for you. If you want something to just work, use the Yelp Compose network, right? And it doesn't sound like a great trade-off, but everyone seems happy. You know, solve the 80-20. So network problems are solved. And you know, this isn't a just joke. This one, well, I mean, there were some systemd units and an enormous bash script, but I'm not going to get into that. So we've got the situation where we can just change the Docker host environment variable, and people can get on with their day, right? Which is obviously nice in theory. So the thing about this compatibility API is, you know, it's a best efforts thing, right? And so we had to backport a whole bunch of patches from upstream in order to fix various different bugs. I'm not going to go into all of these, but what I am going to go into is the one that we didn't backport, because it's the funniest one, quite frankly. So the way that Podman is shipped, it's not just one big monolithic binary. It's actually a bunch of different like OCI libraries and things like that. So it's shipped as multiple packages. So every single HTTP client in the world likes to hit up a version endpoint more than it should have to. The way that Podman knows which version of these various packages it's using is by hitting up your package manager. And I don't know if you know, dpackage is incredibly slow when you query it. So we were having things like timeouts on acceptance tests, performance wasn't looking great. So this is a typical me solution. I basically went, well, all of our packages are managed by a configuration management anyway, so when it does its run, let's just have it splat out on disk like the 4 packages and their versions in a text file, change this to cached dpackage instead, and it basically just spits back anything that's in that text file for any like argument of package. If it's one that's not in the cache, it just forwards onto dpackage. So we basically did an end run around this whole performance problem by just going, yes, this is dpackage, honest. Other API problems, you know, we largely found during like the rollout, and you know, problems with our implementation, because it is by no means perfect, right? So we additionally enrolled a small group of people, usually the people with the weirdest use cases. So that, you know, your people like your production engineering, your release engineering team, those sorts of people who are likely to be doing weird things with containerizer. And we set it up such that they would have their Docker host set to this Podman socket, but we gave them the ability to just unset it. This was a great way of getting people to come to us with their bugs, but then to be able to unblock themselves when we did not immediately know the answer or have a fix. We also wrote a proxy called doc.prox, right? This is basically just a TCP proxy that logs metadata about the calling process. So what we do here is every time that something talks to the privileged Docker socket, we log that command, we log the current working directory, and we log the username. Or we log the login UID, sorry, because that's the bit that you can't cheat around, right? And so what this enabled us to do is, so firstly, we just set this up in logging mode. Then we added in the functionality for it to be able to actually do Auth-Z decisions based on your group memberships forwarded to Open Policy Agent on the host. We set this up in a soft log mode. Obviously, by the time I actually closed that one ticket that had been open for 10 years, the thing that made me go, right, I'm closing this out now is that we'd enabled enforce mode. But anyway, so during this rollout process, we were basically enabling people. We were able to see why are people still using privileged Docker, what workloads are they using it for, and to investigate particularly those repositories and work with the developers to be able to fix them, to make them compatible. This was not necessarily an easy ride. So I wrote a script called Pod Doctor. The idea here was basically we kept asking people for the same diagnostic information. So we set up a script that would basically find that diagnostic information. It would log it all to Slack. So every time somebody came in and asked, they'd run Pod Doctor, it would come into Slack. Then we started to recognize things where we knew how to fix the symptoms. We didn't know what the cause was. So we'd put in that fix. We put in that quick fix so that we could allow people to unblock themselves without unsetting Docker host. So I was able to diagnose and auto-fix the most common issues, post those diagnostics to Slack. And it was basically a living laundry list of all the things that we needed to prioritize to actually fix. We were able to integrate a bunch of those auto-fixes into the core system itself. One of the big issues that we really did find, systemd. Systemd does service dependency management if it's easy. One of the things which I discovered in the course of all of this is that there's a unit in there called, there's stuff to do with like user lingering. And seeing in some of the code base that actually they're shipping units where they're not trusting their own dependency management. It only kind of does the simple stuff. But by and large, it was pretty cool to be able to make so that when somebody logged into a machine, all of this networking, so what have we got here? The base image mount was done, so that's the ID mapped mount. The networking was set up. The user linger stuff is really interesting. I'm not going to go too deep into it, but user linger is systemd's way of going, if you are not on this list, when you log out, we're going to kill all your processes. Unhelpfully, if you enable user linger, it also means on boot, if you've got any user-level units, it will launch them. So we basically had to do some magic around that. And the rest, quite frankly. So to put this in context, there were 2 epics with 212 combined tickets under them. This was a labor of love. It was a Sisyphean task. And that's all of the stuff that we didn't just fix, based on people coming to us. But I'm not going to go through all of these. I would say that the funniest one to look at here is wrapping DU and NCDU so that they don't count bind mounts multiple times. Where we're bind mounting in that huge amount of container storage for every user who's logged in. Whenever somebody goes, oh, disk is a little bit full on this machine, they run DU or NCDU with the -X flag because they don't want to cross file system boundaries, and bind mounts don't technically cross file system boundaries, so it just counts them like n times. So we had to do all sorts of weird stuff, right? So did we fix it? This is the bit where I'm an idiot and try and do a live demo again. So, no, PZB, So over here, you can see on this right-hand side, Docker host is set to the Podman socket, running exactly the same command again, and thank you. Really appreciate that. Cool. So yes, we did fix it, and as a kind of symmetrical addendum to the previous example of this, Basically, this is, again, PID3 BCC output, but it's for curl44con.com in an unprivileged container. I have collapsed one level of this just because it was long. But you can see in here that systemd at the bottom is still root, but then it's a user-level systemd unit, which login UID is me, right? So that means that once that login UID has been set, every child process has that set. Not even root can change it, right? So going all the way up to the curl44con.com command, and one of the things that you'll notice is I did use the nobody user again. That username in there is not a username. It's a really high UID because it's one of my sub-UIDs, right? So effectively, that's to kind of demonstrate how the system works, right? So reflections and lessons, and I have actually left myself enough time for this. What would I have done differently? I really like talks where people are honest about the stuff that they did wrong, right? Because it shows that they actually did a thing. If I were to do this again, I would use roughly the same approach, because I'm like, we get like 1 to 2 support requests a week about, it's specifically with the systemd stuff and the image cleaning. Sometimes it can get confused about those dependencies, and it can delete a file system layer that it shouldn't have. And so it basically wedges that user's containerizer until they come in. Now, they run pod doctor, and it kind of fixes it. Occasionally, we'll have a situation where it actually needs some closer look. And sometimes within networking, it can get wedged too. But the thing is that we're at the stage where we get 1 to 2 support requests a week for this, bearing in mind that we have like 1,000 engineers or something last time I checked, which was not recently. So basically, people are largely able to use this in a friction-free way. I feel a little bit weird that it's not perfect, but that's because I got too many A's when I was young. So basically, like, I think the other thing which I really, really would have changed about this, though, is that I would absolutely have backported Podman 4 to our Ubuntu release. Like, doing this whack-a-mole of different API incompatibilities with no help from upstream was not the one. That said, we weren't going to know that until we tried it. Like, there was no way of really knowing that, like, I suppose we could have looked, but that's kind of looking for problems before you have them. I don't know. Maybe I've learned a lesson here. Maybe not. Would absolutely have written our own service supervision code instead of relying on systemd. We would have been able to address all kinds of complexities a lot more easily rather than doing it the right way. Just goes to show that the orthodoxy is not always correct, or sometimes rarely correct. But yeah, I think the other thing here is that I was working on this project for its entirety, right? A lot of the time it was just me. Later on, my coworker Matteo came in, and he was an absolute godsend because I sling code and he develops code, But I think it's one of those things that I should have recognized in here that this was kind of a bugbear of mine, right? And I kind of took that as kind of quite a personal thing, right? And I felt like I need to do this, and I know that this is a big risk investment, and it absolutely ballooned. But the thing which I should have done here is really respected that the people above me were willing to risk on this, right? And if it's worth investing in success, it's worth investing in failure. So, the whole point here is not necessarily to keep proving it's going to work, to keep proving it's going to work, but like, let's commit to this thing, let's get this job done. I also would have decoupled my emotional well-being from my work because it was a roller coaster. And after the 8th potential technical showstopper, you start to go, maybe I should stop losing sleep over this. And finally, what did we just learn? So leaning into developer tooling and paved paths is absolutely the journey to success and buy-in, and it really helps if you've got a good engineering culture for this. But focusing in on minimizing disruption, choosing the right scope of problems to solve. So like, we didn't solve for the generic containerizer usage. We solved for, we're developing for this platform as a service, right? I'd also point out here that the security industry is really good at suggesting remediation that often costs more than accepting risk. It's very easy when you're decoupled from the people who you're recommending to say, hey, just do this, right? Draw the rest of the owl. Talk is cheap. we need a deeper understanding of the mechanisms underlying those remediations, right? We need to meet stakeholders where they live to actually be able to say, on balance, does this make sense? To be able to comment on that balance. But also to be able to leverage business models and workflows to our advantage. I was able to do that 80-20 because I know Yelp's 80, right? The tech here to remediate a lot of these issues, the right abstraction layer, it's only just maturing. So recognizing that Docker was the new hotness absolutely accelerated our developer velocity, but it comes at a cost, right? The main thing which the parallel I'd like to draw is that over-permissioning allows engineers to not become domain experts in the abstractions they rely on, right? If your root, everything says yes to you, like you don't need to learn about those resources because they are always compliant. Repeating generic best practice security advice affords security teams the same. If you keep repeating least privilege, you don't need to learn about why that's difficult. It's really important to lean into these problems, right? And this is how we should all just change right now, which is obviously nice in theory. Thank you very much for listening to my talk. Before we move on to questions, I'd like to just give a quick shout out to Zach, who repeatedly championed the project, Matteo, who did all of the good work on the project, and Daniel, who's my work BFF and therapist. If you want to find me, my socials are on the schedule. Any questions? Looks like the shock and awe tactics worked.
I was sitting in the audience, so I may have missed it, but why did you move to Podman from Docker?
Sorry?
Why focusing on Podman instead of Docker again?
Basically because of the additional image stores feature. I mean, I would also say that like looking at that feature set, it seems to me that like Docker has kind of stayed at roughly a place where kind of close to where it started. Like they managed to make builds faster, parallelize everything like that. But like from my view, like looking at the voluminous man pages, there were so many more ways in which Podman's also leveraging namespaces and like, you know, various different kernel technologies. So it really kind of struck me that like this was a solution that would at least give us more flexibility in the future. I'd also point out here that our production engineering team had already decided they didn't want to ship containerized system level stuff in Docker. So they'd already installed Podman. So we were, in fact, running it privileged in certain places.
Excellent. Are there any more questions? Yes, hiding to my right.
Hi. I wanted to, we have the same problem. We were looking at solutions. We also use SSSD to bind to LDAP for authentication, and all the UIDs on the system on Linux come from Active Directory, for better or worse. And then an additional requirement is inside the container, users want the same UIDs as outside because of mounts and different types of security on the mounts which require UIDs to map. You mentioned a lot of stuff about the mapping, but I am curious on this aspect on your environment. Like, how do you map external IDs within the system itself? Is it all self-contained? Do you map the same numbers within the container? Do you use the same IDs then outside the container for authentication anywhere?
So, I mean, it sounds like our setups are kind of divergent, but like I'm going to try and speak to the spirit of that a little bit. So basically, like I think one of the really useful things here is like the ID mapped mounts. So you're basically able to kind of solve this at the file system level for the actual file permissions. But like, I mean, so sorry, just to try and understand the problem a little bit better. So you're saying you want the users outside of the container to be the same UID inside the container, right?
The mounts are outside the container. You mount them once per host for obviously reducing the mounts and the complexities there. The users are within the container. The outside host doesn't necessarily understand any of the UIDs within the container, which come from outside.
Got you. So this is like equivalent to you've got like an NFS mount or something equivalent that's on an external system. You want to be able to mount that inside the container. You might be able to do an additional ID mapped bind mount to just translate the UIDs to whatever you need them to be inside the container. So to actually go like, and then use unprivileged user namespaces to basically go, actually your user is mapped to root inside the container, but also so are the files. Or the files are kind of whatever. I think the issue there is going to be like, you're going to need those ID map mounts to be read-write as well, and I don't know like what transitive properties that's going to give right there. But I mean, it sounds like one of those things that like, I think with the mapping for the user namespaces and the mapping for the ID mapped mounts, like it's a bit of a 1-2 punch that you can kind of massage the permissions and massage the way that you're actually interacting with the thing. I hope that's helpful. Or we can talk about it after if you want.
Anybody else?
Excellent. Thank you very much, all.
Thanks.
Whether